In this video, I will be presenting a recursive solution to Chessboard and Queens CSS, and then I'll be proving that this code can be accepted by finding the time complexity in big O notation. So, Chessboard and Queens. Your task is to place 8 queens on a chessboard so that no 2 queens are attacking each other. And as an additional challenge, each square is either free or reserved, and you can only place queens on the free squares. However, the reserved squares do not prevent queens from attacking each other. How many possible ways are there to place the queens? The input has 8 lines, and each of them has 8 characters. Each square is either free, which is denoted as a period, or reserved, which is denoted as an asterisk. Print one integer the number of ways you can place the queens. So for people who do not know how chess work, basically, when you place down a queen, it attacks this. So it attacks basically vertically, and it also attacks horizontally, and it also attacks diagonally. So these are basically the arrows denoting which squares are obstructed from it. So essentially, this question is saying how many ways can we place 8 queens on an 8x8 chessboard such that when we place those queens, no queen is attacking each other. So there's not an arrow pointing to another queen. So for example, I cannot place a queen here because that means it would be attacked, as you can clearly see by the arrow. So this doesn't require us to think that creatively, because what we can do is we can just iterate through all such permutations of this chessboard. So because intuitively there's 8 rows, right? So if there's 8 rows, well, not intuitively, obviously there's 8 rows, but what I'm trying to say, if there's 8 rows, then what we can do is we can iterate through each row. And because, like, here's the idea. If we know that a queen attacks horizontally, then there's no point to check the thing. Like, if I place a queen here, then there's no point to check these squares because they're automatically going to fail. So what we can do is we can uh linearly iterate through row 0, row 1, row 2, row 3, row 4, row 5, row 6, and row 7. And then in each row, we can then recursively check if 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 a column has been marked. Like if I place a queen here, like let's say I place a queen over here. Give me a sec. So if I place a queen over here, in the next when I go to the next row, which is row 1, I can check is row 0 is column 0 already marked with a queen? Is column 1 marked with a queen? Is column 2 marked with a queen? Is column 3 marked with a queen? Is column 4, and etc. In this case, column 0 would be marked with a queen. But then, so basically what we can do is we can have an array called column that basically checks when we linearly move through the rows at that column at I. So at that column of I, where I is an integer from 0 to 7, is that already marked? So maybe we can have some sort of Boolean array. Is this equal to true? Is this marked? So as we linearly move through each row. And then we can say that we also need to check, like, if we place a column, like, we can't just place, like, for example, I can't just place uh the queen here. Just because it doesn't share the same row doesn't mean it's still going to pass. We have to check, does it share the same diagonal? In this case, in this configuration, it's already going to fail. This permutation is going to fail because this queen attacks this queen. So how do we do that? So this is a little bit tricky to observe, but basically you notice that there's 2 types of diagonals when you place a queen. So I'm going to actually use a better example to show this. So if I place a queen like over here, right, there's 2 types of diagonals. There's a diagonal that goes this way, like that has a slope. Basically, you can think of it, there's a diagonal that has a negative slope, and there's a diagonal that has a positive slope. So we basically want to check at some diagonal. We need some representation to check at diagonal 1, which will denote as the positive slope. We need to check at that diagonal, is it true? So we use a Boolean array to check, is this true? And then there's also another diagonal which has a negative slope. So diagonal 2, which has our negative slope. We need to check, is it marked? So when we're linearly moving through the row, and then we iterate through each column, and then we have to see at diagonal 2, is it already marked? And so a way to do this is, if you notice, if I like take the sum of the row and then the sum of the column of the diagonal that has a positive slope, this is 6. And then I take the sum of the row and the sum of the column, this is also 6. And you'll notice that all of these will be 6. So essentially, a diagonal square from the queen's perspective is denoted as taking the sum of the row and column. But that is for the diagonal that has a positive slope. Now for the diagonal of the negative slope with a negative slope, we can do something a bit different. But in this case, we just take the difference, because notice, if I take the difference between the row and the column, or you can, like, yeah, if I take the difference, then we'll have 1 minus 0, which is 1. We'll have uh this I wait okay, yeah, we'll have 0 minus 0, so this should be 0. This should be moved down a little bit more. So we'll have 0, then we'll have 1 minus 1, this will be 0. Then 2 minus 2, this will be 0. So all of these will be 0. So we have to be careful though, because, for example, this is the case where we're checking at some that the difference, it gives us a positive result. We could have maybe a row minus a column, or I mean a row minus a column, or I should say it doesn't really matter. We could have a column minus a row give us something negative. Like if we take the difference of row 7 and column 0, we notice that that's negative 7. So if we try to plug this into like a code, we're going to have like an out of bound. We're going to have an error, right? Because it's going to be out of bounds. So basically, we just shift all the indices of diagonal 2, the one with the negative slope, by 7, so we don't have any errors. And then we're basically going to check, okay, is this marked true? So our that's basically our solution. So we've found representations to see if as we linearly move through a row, is a column marked, is a diagonal marked, is a column marked, is diagonal 1 marked, is diagonal 2 marked, and then if it is, we can place it there. And then once we get to the last queen, so let's say the last queen was over here, once we get to the last queen, we can use backtracking to basically remove that queen and explore other possibilities. And once we've explored other possibilities, we can keep backtracking until we reach the base case. Because once we get to row 8, then all base cases have been, then a permutation of the check of this board that basically can abides by the restrictions of this problem. Once that has happened, then we know that we can just increment our answer by 1, that we've reached a valid permutation. So we can just increment the answer by 1 once we get to row 8. So that's going to be our base case. So let's try to implement this into Java. So we're going to use buffered reader, and I already have throws IOE exception. There should be a bracelet there. So the first thing we're going to do is we're going to import our input outputs, like our IO and util. So then just make sure to do this. Oops. Okay. Then we already have throws IOE exception. Then we're gonna use buffered reader. Oh, dude. Okay. So hold up. I don't know why I'm. Okay. Okay. Use buffered reader, and we'll use new. And I'm going to when we implement it, I'll prove the time complexity at the end. But first, let's just implement this and see. And you'll see that it uh passes the test case. Or actually, maybe I should prove the time complexity now. Okay, so let's actually just take in our input, and then let's like set up print writer and buffered reader, and then actually we'll prove the time complexity. I think that makes more sense to do before we actually do the code. Yeah, it probably does. So let's do system that out, but I already know that it works. So let's derive the time complexity, and then we're gonna so let's actually talk about the time complexity. So what is the time complexity of this code? So time complexity, let's see. So basically what we're doing is we're going to linearly move through each row. And then for each row, so I'm going to try to clear this board. Um, so, and then I'll relabel the axes. I shouldn't have erased that. But let's just try to clear this board. So clear this board, and then we're gonna just quickly just 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7. So as we linearly move through each row, the worst case possible scenario, because remember time complexity comes with the worst case possible scenario, is that as we place a queen, we basically just say that that we have 8 choices to place this queen. Then on the next row, the worst case, like the upper bound case, is that we have 7 places to place a queen, which is not necessarily true. We're just accounting for the worst case. And then the next one is going to be 6, and the next one's going to be 5. So about 8 factorial ways as we linearly move through the uh chessboard. But then we know that we have a constant of 8 here because um as we place a queen, we have to iterate through each square in that row, and there's at worst just 8 iterations. So the time complexity of here is just O of n factorial times n. So we can finally just implement this, which this will pass in CSS. It will get accepted. So let's implement this. So we've already put our print writer. So we're going to need to keep track of three things. We're going to have a static answer, which basically keep track of our answer. So static answer, this should be, I don't, okay, so static answer. And then we're going to have a static Boolean array that basically keeps track of the column. Then we'll have a static Boolean array that keeps track of the diagonal with a positive slope. So diagonal 1 will be denoted as positive slope, so pos slope. And then static Boolean diagonal 2 denoted, which is going to be denoted with the negative slope, so neg slope. And then I believe that's all we need. So then what we're going to do is we're going to create a recursive method called solve, and by convention it's usually called solve. So void solve. And this is basically going to take a parameter called row, because we're going to linearly move through each row. And basically, if we somehow get, because remember, we're 0 indexing here. So if we get to row 8, in this case, we're getting to row 7, but once we get to row 8, since we're 0 indexing, then we know that a permutation has been successfully made that is confined with the restrictions. So we could just increment our answer by 1 and return out of this call. So that's basically how the base case. So this is our base case, right? Once we get to like not there's not row 8, but once we get to row 7, then we increment that row by 1. That means we get to 8, which is not really in there, but the permutation has been successfully generated. So now we need a couple of restrictions. we want to say, oh, also, we need to make sure that we initialize our arrays. I forgot to do that. So column is going to be equal to new boolean. We're going to have, there's going to be 8 columns, 8 like column values. And then for diagonal 2 or diagonal 1, that makes sense to do it first. There's going to be 15 values that we can do. And then that's also for diagonal 2. As you can see, there's going to be new boolean. And if you're worried about like how much are in the diagonals, you could just like size it by something large. Doesn't really matter. So this is also 15. Okay, so we're basically going to check some things. We're going to iterate through once we're on a row, our iteration is determined by a column. So we'll iterate through all the 8 columns. So int I is equal to 0, and then I to 8, then I plus plus. By the way, and I haven't actually taken an input. We'll take an input at the end. I just want to set up the function, because I think that makes sense to do first. In my opinion, maybe it doesn't. Maybe taking an input does. But we're gonna iterate through each column, and basically of that row. Basically, we're gonna check things. We're gonna check if column at I. So if that is true, that means it's being marked. So then we just want to move on to the next iteration. So move on to the next I value. There's no point of checking that. So then and then also but then we also have to check if that one doesn't work, then we have to check if one diagonal one at um I plus the row we're in. If that is there, then continue. Okay, because remember we're iterating through each column, so we use I plus row. That was our formula, right? Column plus row, and that's for diagonal 2. Now we have to check for diagonal 2. But that was for diagonal 1. Now we have to check for diagonal 2. Does the difference? So first we have to add 7 to our answer, and then we have to do I minus row. It doesn't really matter which one we use, if it's row minus I or I minus row. But basically, if this is already marked, then we have to continue to the next I value. And then we also have to check, remember, like in the question, also remember we have to check if a square is reserved. So we have to check that if and this is where we actually should probably take in our input. So we'll take an input called chess. So we'll say static because we need to actually take an input now. So static, what's it called? Okay, why am I blinking out? So static string chess, and then that's just an array, and then we're gonna just take in the input. So we'll say chess.br, or we'll iterate actually um I, and then I plus plus, and then we'll just say that chess at I is equal to br.readline. Okay, so to check if a thing is reserved, since we're just iterating through the column, we just check at chess at I. So at that string, um, right, or it should be chess. It should be chess at row because we're checking a row, right, and we're gonna say dot car at that I. So or car at that column. So as we iterate through each column, if that is equal to um if that's equal to, or technically just use single quotes. So if that's equal to this, then we just continue because that means it's already reserved. Okay, so then if we've like successfully like not continued any of these, what we can do is we can mark that as true. We can mark column as this true. We can mark diagonal 1 as true. We can mark diagonal 2 as true, and then that's basically it. But then we have to recurse onto the next row. So then we have to recurse onto the next row, and then once we've generated a permutation, we have to backtrack. Um, we have to backtrack here by I should, my bad. We have to backtrack here by saying that these things that we set to true is false, because we're just going to backtrack, and then recursion. We'll trust the recursion to generate a new permutation. So we'll trust the recursion to generate a new permutation. So this will be false. This will be false. This will be false. And then what we can do is we can simply solve the recursion starting at 0. We're 0 indexing the rows. And then we can print out our answer. So answer, then close the code. Let's hope we get this on the first try. That would be really nice. Okay, so 14. Oh yeah, I also forgot to do this. Chess. Okay, well we didn't get on the first try. We have to make. I have to forgot to do this. Just a new string. 64 or another. I mean 8. Right. Okay. So let's just put this in there. I don't know why when I make things static, I just like always forget to like actually set their dimensions. Okay, let's go. Hopefully this works. 175. Hold up. What? 175. This is weird. I'm gonna have to debug this. If I can't debug this in a minute, I'll. Is it? Is it? This is weird. Oh. Okay, let me try debugging this and then I'll get back. Hold up. Oops, I had a very small little bug. I just realized I meant to actually do diagonal 1i plus that row, and then 7 plus. So if you caught that, good job, but I forgot to do that. Remember, that's what we're doing. Yeah, now it should work. It should work now. Okay, it took me just like a minute to see that little bug, but it should work. Diagonal I plus row, then diagonal I plus minus row. So, I think I already copied it, but just to make sure. Um, what the heck is this going? Um, oh, and then also I have to, bruh. Okay, I also have to do this. Now that I changed it, I have to do 7 plus I minus row. Okay, now it should work. Sorry for these little bugs. I am doing this live, so like I'm solving it live, so it's not as clean. And so let's do this. Okay, now it should work. Okay, 65. Finally, it actually worked. We just had it's a little small bugs. It's fine, but yeah, that's how you do this problem. I think it's a very nice recursion problem to do. All right, thanks for watching.